Let's get started. Okay, good. Hong Yang, I presume you can hear me. Okay, just a quick recap. We started on the Bayesian reasoning. And basically, if we look at it, instead of saying that if E is true, then H is true, we're now saying that if E is true, then H is true, but with a probability of P. Right? So it means that H will only occur, even though E is true, it can only occur with a certain probability which can be less than 1. So that's the reason why we use E and H here. E basically represents the evidence to support the H, which is your hypothesis. So that is what basically E and H represents. So that's what we talked about in the last week. Before I forget, any questions so far from the previous lecture that you want me to go through again? Or things are still all right so far? So we look at the Bayesian rule that is in terms of expressing it in terms of the hypothesis and the evidence. So we look at the hypothesis that H is true and also H is not true. About it actually represents not H, right? Or as shown here, that the hypothesis H is false. So we look at the and then we also talk about what you mean by prior probabilities. That means that there's no condition attached to it. That is your prior probability as represented here. That means that the prior probability that H is true, the hypothesis H is true, and the prior probability that H is false or H is not true. On the other hand, we also look at something called conditional probability now, rather than prior. Prior, in a way, it means that there's no condition. Whereas in the case of conditional probability, as shown here, so this one is H is true, the hypothesis H is true, given that, E is true, given that the hypothesis H is true, right? So what is the probability or conditional probability that given that H is true, then E is true. So it has to be based on H must be true first. That is your conditional probability. What else? We talk about the prior, right? And then we have users provide the information. So your users will provide the information of the evidence, about the evidence that's been observed, right? And the expert system will then calculate. So this is leading to the expert system based on this Bayesian rule to calculate, to tell the user what is the chance that given that the radio forecast that today will rain, actually it will rain. Or you need to bring, do I need to bring the umbrella given that the radio forecast that today will rain, the hypothesis it will rain. So, and the expert system compute this conditional probability that given that E is true, the evidence shows that it's true, the hypothesis is true with a certain probability, not necessarily equals to 1. So this is your user supplied evidence E. So another, probably another name if you like, other than conditional probability is also called the posterior probability. So these are all the new terms that we come across in the lecture so far. So we have a prior, which is actually no conditions attached, just basically is H true or is H false. Then the posterior actually is a condition. So as shown here, the probability as shown by this equation is your posterior probability of the hypothesis H being true upon observing evidence E. You see E happening, before then you can use that to determine the what we call the posterior probability. So that's what we actually look at, and then we actually expanded it in terms of not just one evidence, but many evidences, and also then we look at also many hypotheses, right? So, but the thing is that don't forget that all these has to be all these probabilities, right? All these conditional probabilities for all the possible combination of all your evidence for all the hypotheses, right, has to be obtained from your expert. So the expert, in a way, this will place an enormous burden to tell for the expert to tell you what's the number, what is the conditional probability for that. So therefore, it places an enormous burden. So that in a way is saying that this one actually doesn't work. Doesn't work, because it's another. It's difficult to get the numbers. So instead of that, instead of the previous unworkable equation, we then expanded it and I got this. So this is only based on one hypothesis at a time, rather than expanding it one hypothesis and one evidence. So you have E1 HK, and K can be 1, E2 HK, and then so on and so forth. Right? That's how you look at it. So basically, this is just expanding it. Right? So if you expand this one, this part here, that's how you get this. Basically, this is expanding the part here to get this. Okay, now, that is the part here. That is where we stop. Okay. So let's look at the how do we rank the potentially true hypothesis, right? So it's still potentially true. We do not know yet, right? So it potentially can be true. Now let us consider a simple example. Suppose an expert given 3 conditionally independent evidences. The evidence must be independent. It cannot be each of them cannot depend on the others, right? Either one or other 2. So those conditionally independent evidences, E1, E2, and E3, then create 3 mutually exclusive and exhaustive hypotheses, H1, H2, H3. So as a result of these 3 independent evidences, your E1, your E2, and your E3, result in 3 mutually exclusive, right? Again, mutually exclusive and exhaustive hypothesis, which is your H1, H2, and H3. And therefore provide, and also provide, the expert also provide the prior, right? What's prior? If you remember, prior is your unconditioned, no conditions attached. That means it's just that H1 is true or false. Of these 3 hypotheses, H1, H2, H3. So there are H1, the prior probability of H1 being true, prior probability of H2 being true, and finally, prior probability of H3 being true, respectively. In addition, the experts also determines the conditional probabilities of observing each evidence for all possible hypotheses. So the expert will also need to determine the conditional probabilities of H1 and E1, and so on and so forth. So you can actually draw a table for this. Now on the top here, the right-hand side 3 columns here, rightmost 3 columns are your hypothesis, H1, H2, and H3. So there are actually 4 rows because of the fact that you have 3 evidences, E1, E2, and E3. E1, E2, and E3. So if there's now the topmost row here, the first row here, looks at the prior probability of the hypothesis H1, H2, H3 being true. So this has to be supplied by the expert. So what's the chances of H1 being true? So this is unconditioned, no condition attached, no condition of anything else. So just is 0.4. This is 0.35 and this is 0.25. And all of them add up to be 1. Now, the next row now, the second row, what do you see? Now you can see that what is the probability? Now this is conditional. All trees will be posterior, right? Remember that we actually introduced a new term now, a new name called posterior, which is your conditional probability. So in this case, you can see here, what is the probability of E1 being true given that H1 is true? Right? So we look at this. So it's given as 0.3. So the expert got to fill up this one, right? So now you continue and look at E1. What's the chances of E1 true given that H2 is true now? H2 is true. And then finally, E1 is true, H3 is true, which is 0.5. So all this is going to fill up. Now, assuming we first observe evidence E3, right? E3, just the evidence alone. So the expert system will then have to compute the posterior probabilities for all the hypotheses as shown on the next page. Right? This is how you calculate. Now I want to notice this is a H1 E3, right? So I got I have the evidence. I can what do you call it? I see I have the evidence that E3 is true with some probability. You should observe E3. Now notice here, some of you may be wondering what this one and this table and this one seem to be the same. No, it's not, right? So you can notice that this is actually your given information. Now, from the given information, I want to calculate what is the conditional probability of H1 being true, given that E3 is true. So actually it's the flip, right? So E3 being true first, then I want to calculate what is the probability of H1 being true. So to do that, you go back to your Bayesian rule. So it's given as such here. So basically, the Bayesian rule for E3 being true, Hi being true given that E3 being true. So this condition, based on the condition that E3 must be true first before I calculate what is the chances of Hi being true. It's given as this, as shown here in this equation here. So it actually is probability of E3 being true given that Hi being true multiplied by the prior probability of H1 being true divided by the summation of all these combinations, right? E3 H1, E3 H2, E3 H3, right? And then you calculate this. So this is expanded here. Now, all this value, if you expand this, it will be E3 H1, right? Flip, right? E3 H1 multiplied by the prior probability of H1 divided by E3 given that H1 is true, right? E3 given that H2 being true, and finally E3 and E3 being true. Let's go back to the previous table, right? You see here, so it's E3 0.6, 0.7, 0.9. 0.6, right? This is your E3 H1. E3 H2, 0.6, 0.7, 0.9. And then this will be the multiplied by this part, which is your prior probability, no conditions of H1, H2, H3. H1, H2, H3. So then you do it for the next one. So this is only for H1, E3. I also want to do it now for H2, E3. And then you substitute values inside. Now, here you can see the only difference is your E3. Since it's H2, E3, H2. E3, H2, 0.7. 7 multiplied by the prior probability of H2, which is 0.35 over here. Right. So all these values you can see here. I want to calculate something new, and then I base it on the values that I can get, that I'm able to get. So this is based on these values. So you can see here. Now, one thing I want to point your attention here, the denominator here, the bottom row, right, are all the same. Only top part is different because top part will be just the E3H2, right, or E3H1, E3H3, right, and that's how all you get it. So you compute this, calculate this, you get these values here, 0.34, 0.34, 0.32. Now, what can we say about these values? You see that after the evidence E3 is observed, that means you observe E3, the belief, that means that the probability of H1 being true based on E3 being true first. Those believe in the hypothesis H1 will, this is H1, H2, H3. So it decreases and becomes equal to the belief in hypothesis H2, right? Now, belief in hypothesis H3 increases, and even H3 increases and even nearly reaches belief in hypothesis H1 and H2. Conditional probability that we want to calculate are as such, right? So you have Hi being true given that E1 and E3 are true. So this is how you expand it to this form of the equation. So once you have the equation, then you expand it, and I think this is what you get, 0.49. Now, you see that the hypothesis H2 now has become the most likely one, which is 0.52, right? So after calculating now, so because this one is based on the expert system, so what's the chances of H21 being true given that E1 and E3 are true? So with those other hypotheses, so you can see that H2 now increases to 0.52 now. Why do you think why has H2 increased? Why? So now finally we have the E2. So we have E1, E3, right? Just now we started from E3, then we have E1 added to it. Now we have E2 added to it. So what is the condition now? Condition probability. So that is the condition of what's the probability of or belief in Hi being true given that E1, E2, and E3 are true. So this is what you, I think this is actually straightforward, right, from the equation. So again, you don't have to worry about memorizing this because you can always refer to these equations in your calculations. So once you do that, you find that what's the chances of H1 being true given that E1, E2, E3 is true or are true? So there's 0.45, and you do it for H2 now, which is 0, and then the last one was H3, which is 0.55. Now, although the initial ranking was H1, H2, H3, what does it mean by that? It means initial ranking was, right? You can see here, ranking means that which one has the highest score? Probability, right? Probability of of it happening, right? So it's actually H1 is the highest, 0.4, and decrease of H2, and then which is more than H3. So 0.4, 0.35, 0.25. So it's H1, H2, H3. So that was the initial ranking of the that was the initial ranking, right, from the previous table. And it's what else? It's prior. It doesn't rely on any conditions. So this is the pure sort of probability, if I may say so, right? Another way looking at it. So it's H1, H2, H3. Now, once you have all the new evidence coming in, your E1, E2, E3, right? You find that the only hypothesis H1, H2, H3 remain. Because why? You can see this is actually 0, means that it will not happen. absolutely impossible, right? Zero, right? So there's not even a slim chance, no chance at all that it will happen. So now you have your, so after only H1, H2 remain, right? So this was the initial ranking. So it has changed now. What does it tell you? Tells you the Bayesian method has some biasness. Let's look at it now in more details. The framework, right? The method that we use for our expert system based on the Bayesian reasoning. So the framework for the Bayesian reasoning requires probability values as primary inputs, right? So you need to have those probability values. So you need to get it from expert, right? So again, this one goes back to our, remember the structure, the form of the team, the main players of your expert system. There are 5 of them, remember? So we need to get those values, and then you get those values from the expert, who is a human, right? So again, now these values are the values given to you, right? Involves human judgment. So what's the chance of you doing something, right? So you say, what's the chance of me doing something? So that one has to be given by the expert. Now, again, I think later on we talk about this. Now, however, the psychological research, right? So there's some study being done by the psychologists, and they publish it in these 2 papers shown below here, shows that humans cannot elicit probability values consistent with the Bayesian rules. So I think for some of you, you might find that there's a new word here, elicit. That means cannot produce, cannot tell you, cannot give you probability values consistent with the Bayesian rules. That is, that follows the Bayesian rules. So basically, what it means is that, if I may say so in a more simpler term, is that the humans, as humans, we cannot give you those values accurately, right? That is consistent with the Bayesian rules. So this suggests that, and this is actually not just any comment, any what you call casual comment, as they say in English. Casual comment, that means a chit chat. You just say, "Oh, I believe this is so." We are all allowed to give comments. We give our views, but this is actually based on actual hard scientific data, based on psychological research, psychological experiments, and then published here by these 2 persons, and you can actually check it out, right? So we find that humans are not so good at that, given actual good values that is consistent with the Bayesian rules. So what does this mean? It means that it suggests that the conditional probabilities may be inconsistent with the prior probabilities given by the expert. And what does it mean here? It means that the expert will give you the prior probability. What's the chance of it raining, right? What's the chance of it, what else can I give you? Raining today, I will strike lottery tomorrow, right? Things like that. But that one is given by the prior, it's actually prior probability, just one event. The condition means that what's the chance of it raining, given that the weatherman, the radio forecast that today it will not rain. Right, so this is based on condition. So again, it's not easy for the expert to give you those values. So the 2 values are not the same, are not equal. So this is difficulty of given by the expert. So here, so I think I want to maybe the word is impress you, just to tell you that this conclusion that humans cannot give you accurate probability values that is consistent with Bayesian rules in the psychological study is actually from experts, among which is Daniel Kahneman. If you look at here, over here, right? He's actually who is he? He's actually a psychologist, he's an Israeli American psychologist, and looking at his work, his research work is on psychology of judgment and decision making. He studies how humans make judgment and how humans make decisions. And he was the 2002 Nobel Memorial Prize in Economic Science. So he was a Nobel Prize winner for economic science in 2002. Right. So that is that's why we respect the findings of his work over here to say that humans cannot give you good probability values that is consistent with the Bayesian rules. Now, let's now look for example how this works. Now consider, for example, back to our earlier example of a car that does not start. Your car cannot start, what happens? So, and then your car cannot start, first condition. Second thing is it makes odd noises when you press the starter. So cannot start, of course, you start means you press the starter. The conditional probability of the starter being 40 if the car makes odd noises may be expressed as such, as shown below here. Right? So what is the condition that the starter is a problem if the car makes odd noises? Right? So if this kind of knowledge, how would you express it? You express it in this form to capture the knowledge there. So if the symptom evidence is odd noises, then the starter is bad. Right? So if you remember, this one actually we look at this example before a few lectures away from I know recently. Now this one's actually now with a probability of 0.7, not 1.0, not for sure. It's only 0.7, right? So can see. So if the symptom is the evidence is when you press the starter, there's a strange sound coming from the car. Then you suspect the starter is bad, right? Based on this probability. Now consider again the same example. A car that does not start and then makes noises when you press the starter. The conditional probability of the car being 40, if the car makes noises may be expressed as, this is condition now, this one is actually prior. The posterior probability or conditional probability that the starter is not bad given that the car make the starter makes out the starter makes some odd noises equals to it's the same, right? I think they're just playing the words. Not bad means actually means good, right? So equals to the starter is good and but the car still give odd noises. Excuse me. So top is a bit different. So this one's actually so just actually equals to 0.7. But this is the starter is bad, right? And the car and the symptom is it make odd noises, right? So make odd noises and then the starter is bad. So what's the chances of the starter is bad, given that the evidence is that there's some strange sound coming from the car when you start the car, which is 0.7. So this one, if it's good now, it will be 1 minus this, right? So because both of them to add together to be 1. So basically what we are saying is that if the starter is good, what's the probability of the starter is good, given that there are odd noises, making the car making odd noises equals to 1 minus P of the starter is bad, given that the car still make the same bad noise, odd noises, strange sounds. Therefore, we then obtain this companion rule that states that if the symptom is odd noises, evidence is odd noises, then the starter is good. Means that what's the chance of your car when you press the starter, right? It still make odd noises. The starter is good given that the car still make odd noises, still making the strange sounds. Can you follow? I think this one needs a bit of time maybe just for some of you, not all of you. So this one actually is 0.3. So this is actually calculated from the early one. So this is your companion rule now. Right? So the first one is the car make odd noises when you start the car, and you believe the starter is bad, which is 0.7. So if what's the chances of the car still making odd noises, but now the starter is good, which is 0.3. Now your domain experts, the experts that you talk to, in this case will be what? Your mechanic, right? Such domain experts do not deal with conditional probabilities, right? So you can ask a mechanic, what's the chances of the starter is good, given that when you start your car, it still give you funny sounds. Those kind of things is condition. Condition is the car making strange noises. So such experts cannot deal with that. Cannot give you some estimate of the probability. So here in this case, often deny the very existence of the hidden implicit probability of 0.3. So probably this one, the first case here is starter is bad, odd noises. So this one maybe they can give you, but again, they have difficulty giving this the probability of 0.7. Now they cannot. What this is saying is that they cannot even give you this. Sir, what is the starter is good, but the car still make odd noises, funny sounds when you start the car. This is what you call your. They will say this one will not happen. If your car is starter is good, your car will not give you any strange sounds when you start the car. So this is your. They deny. They don't agree. They will say no. This will never happen. But in our case, we want it to we measure this to be 0.3, as for example. So we actually calculated back from the earlier case of 0.7, and then we get here the 0.3 from that. We would also use available statistical information. Maybe now you begin to see why statistics is so important in engineering and science. So we will also use such available statistical information and empirical studies to derive the following rules, right? So based on the study, based on the long history, especially if you visit the mechanics, the workshop, the car workshop, to find out how many times the car came in and the customer complained that the car is making strange sounds, and then when you check, actually the problem is not the starter. So that one is something you can actually information that is there in the workshop, because I think if they're working for a few years, so they will have these things. Maybe especially if they have keep a good record of the solutions to the problem, so you can actually collect that. So assuming that in this case, right, so it's actually 0.85. So we find that maybe close to 90% of the time, if the car is making strange sounds when you start the car, it's actually due to the starter is bad. So you just the workshop just changed the car starter of that car. In addition, the same as before, but the starter is bad. The symptom is that it doesn't make any strange sounds when you start the car. But finally, the mechanic found that actually the starter of the car is a problem, and that's actually 0.15, small probability, right? Can you see that? Because the car, when you start it, there's no strange sound coming from it, odd noises, and then finally you find the cause of the problem is actually your starter is no good, right? But it's keeping very quiet. So to use the Bayesian rule, to use that, we still need the prior probability, which is your probability that the starter is bad if the car does not start, right? So what's the chances of the starter is bad if the car does not start? We need that. So suppose in this case, suppose the expert now, the domain expert, which is a mechanic, tells you that this value is 5%, 0.05, right? So therefore, we can now apply, which is this one. Remember, this is actually based on this 0.85, right? Starter is bad, given that it makes strange sounds, odd noises when you start the car. But remember the Bayesian rule. You need the other part, which is your prior probability of the starter is bad if the car does not start. This is actually we talk to the expert. What's the value? He or she give you 5%. So you put it inside this equation. So now we can calculate the Bayesian rule for what are the chances of the starter is bad, given that the car gives you odd noises when you try starting it. So it's due to the starter is bad. What the chances of the starter is bad, given that the car makes strange sounds when you start the car. So when you put these values inside, right, this is 0.05. Of course, the not true will be 0.95 over here, right? So again, the same here, 0.85, which is here, right? And then this, the starter is bad, but doesn't make strange sounds, which is 0.15, which is over here, right? Not the starter's problems, right? So you have this that. So and you find that actually it's actually 0.23, 23% probability that is actually the starter is bad. Now this number, if you look at it, it's actually much lower from the 0.7 given at the beginning. So the starter is bad because I think the starter is bad given that the car makes funny sounds, odd noises when you start to select as 0.7. This was actually given by the expert, domain expert before. Now, when you calculate all this, when you put in the new values here, actually it's only 0.23, not 0.7. So you can see a big difference now, 0.23 and 0.7. Now, what's the reason for this? The reason for this inconsistency, right? The two values are not the same, is that the expert make different assumptions, right? The experts make some assumptions when looking at these conditional and prior probabilities. That means the posterior as well as the prior probabilities. Of course, he or she will not tell you, but I guess when you ask the person, what's the chances of the starter is bad, given that the car, when I start the car, has this making odd sounds, odd noises. So in the person's mind, when they give you this number 0.7, he or she would have made certain assumptions, right? So certain assumptions. Of course, unless you ask him or her, you will not know what those assumptions are. So it's very important actually in asking these things. What makes you give it 0.7? Can you tell me how you arrive at the number 0.7? What are the assumptions? So it's a result of this when looking at this prior and the conditional properties. So that is one of the weaknesses of the Bayesian rule to calculate the to give you a probability of the event happening based on certain hypothesis, right? Or the other way actually, based on the evidence, what is the chances of certain hypothesis being true? So this one completes the section on Bayesian rule. All right. So result of that. So we want to look at, is there something better for us to use, right? So there are, I think you can see here, one of the major problems is that it's not easy to get the probabilities from the domain expert to get, because you need those numbers for you to do the computation, the calculations. But it's not easy to get those numbers from the expert. So what's the alternative? What is there a better way of doing things, of solving this for my expert system? So one of them is actually your certainty factors theory and what we call evidential reasoning. Certainty factors theory and evidential reasoning. Based on the evidence, we reason, we come to a conclusion. Let's look at it for the next few slides, what this is all about. So certainty factors theory is a popular alternative to your Bayesian reasoning. I think clearly you can see that there are some challenges, some weaknesses of your Bayesian reasoning. So therefore, to overcome those weaknesses of your Bayesian reasoning, it has been proposed that certainty factors can be an alternative. And so far, it's also a popular alternative. You'll see later on why that is so. Let's look at it now. Going to the certainty factors theory. What is it? So first part is your certainty factors, which is represented by the initials, by the letter CF, representing certainty factors. What is that? There is a number to measure the expert's belief. What is it? Actually, it says that the experts believe in this being true, right? So I want to measure that. How do you believe? What's your belief, right? To measure your belief in that certain event, right? So the maximum value of the certainty factors is say 1.0, right? Of course, you can change this value to something else, but I think for simplicity, we actually always use +1. So +1 represents definitely true. And then the minimum, the smallest value, so it's no longer 0, but it's -1. -1 representing definitely false. So for example, now, if the expert says that some evidence is almost certainly true, now you can see already why we have to, why early on we did the study on the what you mean by almost, what you mean by never, what you mean by certainly, right? So almost is actually not the same as certainly true. So almost certainly, so you can see it's actually close to certainly true, which is 1.0. So in this case, you will assign a value, a certainty factor value of 0.8 because it's only certainly true, almost certainly true, right? Will be assigned to this evidence. So, for example, going back to our earlier example about the weather, if the weather radio forecast that today is going to rain, right? You then assign a value now to that, which is 0.8. It's not 1.0. It's not completely true. If I may say so, use the word completely true. It's actually almost certainly true, which is 0.8. So now it's assigned a certain value, no longer so 1.0 as we assumed in the past. Right. Now let's take a small deviation from the discussion so far. Let's look at the example of a application of a rule-based expert system. This was actually based on this system called MySyn, was developed by two persons, Edward Shortleaf and Bruce Buchanan, in 1975 as an basically they call it artificial intelligence, AI application in medicine. So this is a rule-based system in medicine. What does it do? It is an expert system for the diagnosis, right? Identify the problem and the treatment, right? It also tells you what's the problem and tells you how can you solve the problem of blood infections and another a disease called meningitis, based on blood infection and meningitis. It's actually conducted. This expert system will talk to the patient, right, in a text-based. At those times, we don't have this graphical user interface, right? It's so text. So you type in your answers to the questions, right, with a so-called a physician. Right? So this is your expert system. So the expert system will become your online, will become your artificial doctor. Now, what does the database consist of? The database consists of a few things. Among them is the knowledge, right? If you remember, we define knowledge in the expert system as a set of rules that is captured by interviewing with the doctor. Now, this set of knowledge will be based all about infectious diseases, particularly bacterial infections. The disease caused by bacterial infections. It does not explicitly diagnose the disease. It means it doesn't tell you exactly the actual disease, but it will prescribe, right? It will tell you the medicine to take on the likely causes of that bacterial infection, of the disease you have, of your health problem, right? Likely causes. Again, you can see here, we're not saying that it's always true. It's most probably true that you have this disease, you have this sickness, right? So I think we don't have that, isn't it, in the current situation whereby you are tested positive, there's no number attached to it. So we assume it's always 100%. But I think you see already in the media, in the newspaper, that is actually, we are actually moving away from that and going into I think class 1, class 2, type 1, type 2, type 3, type 4, and type 5 type of infection. Okay, now, then in the MySyn, this particular system, MySyn, you have also, there's a certain factors assigned to those uncertain terms. Let's start with the top here, which is negative, which is definitely not. So if you use the word definitely not, right? So here that means you don't have that problem, right? So we actually assign a value of -1. So I suppose the system will ask you, or maybe not ask you, but will maybe ask you to select any of these. So at the back, you will calculate, you assign a certain factor, CF, to your answer. Are you feeling feverish? Then you say definitely. I think this is something we see in your Meister-Jatra. Are you feeling feverish? Do you have cough? Do you have headache and things like that? Right. So if you say definitely not, the system will assign a certainty factor value of -1. Almost certainly not, right? So it's close almost. So it's close to definitely not, -0.8, probably not, -0.6, maybe not, -0.4, and unknown. So this is unknown section, -0.2 to +0.2. This is a range which is similar to what you study in your digital logic circuits. That is the undefined zone, undefined region. So undefined region here is -0.2 to +0.2. Of course, you as a developer can also change it. If you want to put it something else, you can also put in maybe, maybe not. Then 0.2, and then the unknown can even be shortened, shrunk, decreased in size to just -0.1 to 0.2 if it increases your accuracy of the system. Then moving to the positive side, maybe is 0.4. Probably is 0.6, almost certainly is 0.8, and then definitely is 1.0. So you can see here, actually this is a mirror image of the one at the top, or the one at the top is actually a mirror image of the one at the bottom. So this is negative, this is positive. So you can see they are the same values. Let's say just replaced by this is replaced with with an extra word, not. Maybe not is -0.4. It's just maybe it's 0.4. So this is how you assign your certainty factor value to your MySim system. Now, that was the how we actually use the built expert system in MySim, which is for identifying the what I call the bacterial infection disease. Now, when you use the expert system with certainty factors, the knowledge base, right? The knowledge base, which is remember, you have your database, which is your actual evidence, your actual real-time data, and then your knowledge base, which is actually the information you collected by interviewing the expert. So in this case will be your doctors, and then this consists of a set of rules. So the knowledge base will consist of a set of rules that have the following structure. Again, nothing strange. It's the same as before, except that now there's something here at the side, which is your CF, or your certainty factors value, where this CF represents the belief in the hypothesis H, given that evidence E has occurred, right? So you look at it closely, it basically says that if E is true, so you actually see it true, right? So for example, maybe one example would be if you actually see rain, it's raining now. So it's actually, if it's raining, then the hypothesis is that would it rain? Of course, it will be, this value will be quite high, right? So this is the hypothesis is based on the evidence that you actually collected, right, from the environment. Now, the certainty factors theory is based on two functions. Basically, the measure of belief, how true is the event, right? Measure of belief will be based on the hypothesis and the evidence. And then at the same time, there's also the other side, which is your measure of disbelief, right? The not part that is not true, right? Measure of disbelief. Let's look at it. So measure of the belief is actually if your prior probability of a hypothesis is true, then your measure of belief is actually equals to 1. H and E is equal to 1. Otherwise, it's based on this equation here. I'll come back to this later on. Now, on the other side, you have your measure of disbelief. Same thing again. If your measure of if the prior probability of your hypothesis is actually false or 0, then your measure of disbelief of the hypothesis and the evidence is equals to 1. So this is only based if your hypothesis is actually your prior probability of the hypothesis is actually false or not true, 0. Now, let's look at the one here. Let's start with the one on the belief, measure of belief. Now, if your prior probability of the hypothesis is no longer equals to 1, no longer true, somewhere in between, right? Anything than 1.0. You use this equation to calculate. Now, how do you calculate this? That's so you have here, you have your max of your, okay, you have your prior probability. Prior probability of your hypothesis being true. You compare that to the prior probability of the hypothesis H being true, given that evidence E is true, right? The larger of the two, the larger value of the two, minus the, then this will minus the prior probability of hypothesis being true, right? And then divided by this function at the bottom here, right? And then the reverse is also true for the other part. That is the minimum of the smaller of the two values here, minus the minus the prior probability of the hypothesis being true. Oh, sorry, being, yeah, the prior probability, not true or false, just the prior probability of hypothesis H, right? So this one actually explains what each of these symbols represents. This is your prior probability of hypothesis H being true, P of H. And then this is the conditional or the posterior probability that hypothesis H is true, given the evidence E is true. Let's look at it. Now the values here as a result, you can see here, this values here. So it's either 1 or 0, right? So it ranges from 0 to 1. So both of these can lie between 0 and 1. Now the strength of belief or disbelief, how strong is that belief or disbelief in your hypothesis H, depends on the kind of evidence E is observed. What do you see? What do you get in your evidence E? Some facts may increase the strength of belief, but some facts will increase the strength of disbelief. Of course, this is based on the equation there. Depending on the value for your evidence, those will change. Of course, this is something that we can always is clear. The total strength now. So from the measurement of your measure of belief or disbelief, MD or MB, can be used to calculate your certainty factors, as shown below here. So this will be based on the measure of the belief minus your measure of disbelief, divided by 1 minus the minimum value of either the belief or the disbelief, which is a smaller one, right? So remember, right, because I think if you don't do that, this one will actually give you a value which is 0. 1 minus 1 will be 0. So this one actually, that's how it works. As a result, you get this value, and then you get this to be smaller than 2, so this will be some finite value, not 0, right? At 0, then becomes the certainty factor becomes infinite, which is not logical. Example now. So I think let's look at example. So moving away from your measure of belief and disbelief, now we want to use the certainty factors, CF, to use it to calculate, to actually use it to actually get our expert system to tell you some useful answers, give you some useful answers. So consider a simple rule, that is, if A is X and then B is Y. So the expert may not be absolutely certain. The expert cannot be sure that this rule is correct. If A is X, then B is Y. How true this is? So he will say, I'm not so sure. Now, furthermore, suppose it has been observed in some cases, right? In some cases, even when the if part, this part here is satisfied, if part of the rule is satisfied, and the object A takes a value of X, right? X, A is equal to X. That is true, satisfied, right? Object B can acquire some different value Z, right? So what it means is that if A is X, A is equals to X, but your B may not be Y. B may be Z, right? So as a result, we then have to change this rule now, using the certainty factors theory. So if A is X, right, then B is Y, right? 0.7 with a certainty factor of 0. Most of the time is actually true. And then another one is actually this is it can also be Z, but this is only 0.2 with a certainty factor of 0.2. So you can still see that. So the certainty factor assigned by a rule is propagated through a reasoning chain. So later on you see how it works. So this one, once the certainty factor calculated from one rule will then be used in the subsequent calculations in that reasoning chain to arrive at the final answer. This involved establishing the net certainty of the rule consequent. That is the then part, which is a consequent. Remember, we discussed this before. And the evidence in the rule antecedent, this is your if part, is not certain. So the CF of your H and E equals to the CF of E multiplied by the CF. So I look at this in the example to clarify this further. For example, if the sky is clear, right, then the forecast is sunny. Forecast is that if the sky is clear, this is your evidence. And the hypothesis is that your forecast should be it will not rain, right? The forecast will be sunny. It will be sunny. This is 0.8. And the current certainty factor of the sky is clear is 0.5. That is the sky is clear. The certainty factor for that information is 0.5, right? So this is your sky is clear is 0.5, right? That's the evidence. This is all equals to 0.5, and then your CF from this. So the CF here refers to the certainty factor of your rule of your knowledge from that rule, right? So you multiply the two together. So the certainty factor of a sky is clear, which is your evidence, right? It's 0.5 multiplied by 0.8. So then it comes back to be 0.4. Now, how to interpret 0.4? Right, 0.4 with something maybe, right? So you can actually translate back to your certainty factors. So this is based using the same interpretation as Bayesian, right? So if it's minus 0.4, it will be maybe not. So if it's 0.4, it will be so you can see here it's actually 0.4. So it's actually maybe sunny, right? So because 0.4 is maybe. So imagine if you have some other larger value, it will be say probably sunny, almost certainly sunny, definitely sunny, for example. Okay. Let me see here. Okay, I think we will stop here because this one I'll need some time to go through because I can see is I can't simply rush through. I will rush through, you'll find that you will not able to understand. So I will stop here and continue on Friday. Is that okay? Because I believe also you guys have a class to go after this. So are there any questions before we stop? Our assignment group member confirm. Okay, group member, good question. Good. Actually, I will have to look at it because I have a few students. I think I have two conditions. No, two observation, right? Ken Long, let me answer you the first. Okay, answer the second part. Ken Long, as I said before, your lab report submission is 2 weeks from the day you do your lab itself. So assuming that you did your lab yesterday, it will be 2 weeks on or before, right? That means the latest date it will be when you come back for the next lab. You should have your report submitted, and I will share with you later on the Google form for you to submit. Now back to your first question, which is assignment grouping. As I said, unless there is actually impossible. That means that there's an odd number in your class. I don't think you guys will. I don't think you guys can work with a different program student. That means that EE student probably will not want to work with the MA students. So I don't think that was possible. So now, what's the size of your class? If your class is actually odd number, that means that there will be maybe one group. I will only allow one group with an odd number of students, 3 per for the group in the assignment. The lab report is individual. So I understand. I think I'm not sure whether your EE students, it is I know one of you actually have left the program and joined something else, do something else. And the other one, I'm not sure whether it's still here. I think core is it? Core something is still here. Otherwise, if it's still an even number, so I will expect you to have 2 per team. So please check with your class rep what is your total number of students. Even number, that means that I will not allow 3 per group or 2. Right? If it's an odd number, then first come, first serve. I already told one group. So what first come, first serve, odd number, I can allow that. But I think this is based on the earlier assumption at the start of this semester when I thought there was an even number. I think 50 of you, but I think the number has dropped either to 49 or 48. I'm not sure. I need to check. Right? So far, I think it's 48 of you. So please find first of all, check with your class rep. Christopher, yes. This one, I think, hold on, because if I brief you now, it's no point because this assignment is based on the fuzzy logic. So maybe after next week, I will start briefing you on the what you call it, the assignment. The assignment also, I need to, I think I need to find extra time. I don't want to interfere with your lectures because as it is, I'm going very slowly this semester. So you can see here, I'm covering already four lectures already on this certainty factor. So I'm going quite slow, right? So please check with your class rep what's the total number of your students in your class, and then appropriately find either 2 or 3. 3, you have to come back to me because I think again your grouping. I think to be fair, it will be on a first come first serve basis. If you quickly say I want to have 3 per team, then I will allow that. Only with the assumption there's an odd number of students in your class. Otherwise, I will still stick to the even number per group. Okay, so I think Ken Long, does it answer all your questions? Right? And I think you guys have to go off for your class, right? So I'll see you tomorrow morning. Okay, bye bye.